If you're looking for the world's most detailed solar imagery and the most comprehensive space weather, you've found it. Welcome to the Daily Space Weather Show here at the Smash News Network, least busted name. In news, that's a 24-hour video featuring SDO 131 angstroms difference imagery along with 304 angstroms ionized helium along with that ionized iron. And that is the T-mass, the most active portion of the closest star. I'm pretty sure we said yesterday the most active sunspot would indeed be that one, well, be the northwestern limb in general, and there you have it. Here is the equatorial zoom. Pretty quiet sun over the past 24 hours, and we have some interesting coronal mass ejections to cover as well, and we also have a great Ask a Particle Physicist segment today about coronal holes and how they are the source of high-speed solar wind. Here is December 28th and 29th to date SDO continuum. Mostly stable sunspots there, no major changes happening on the Earth-facing portion of the solar disk. Colorized magnetogram agrees with this analysis. Next, we'll take a brief look at what's going on as far as volcanoes go. We'll be speeding things up very much fast tonight because time is running out, folks. Time is running out. Hopefully not on your ability to tread water in the river Styx. Seriously, though, press the like button. Next, Kluchevskoy is the first volcano to start out our list. This is the rundown. Paroxysm occurring there at Kluchevskoy. Also degassing carbon dioxide and sulfur dioxide coming from the caldera. Sakurajima exploding 7,000-foot ash plume over Kyushu, Japan. Suwanosejima, flight level 060, 6,000-foot ash plume. Ibu, 6,000-foot ash plume. Luotobi, 9,000-foot ash plume as it explodes. Dakono exploding, 13,000-foot ash plume, flight level 130. Popocatépetl exploding, flight level 200. Fuego, ongoing emissions there in Guatemala. Nevado del Ruiz also producing volcanic ash emissions. Revenador exploding, flight level 210 over Ecuador. It's a 21,000-foot ash plume. Not sure about Sabancaya. Please do not pole vault the caldera. Next, seismic activity. Here is the convenient 90-day bar graph, courtesy of volcanodiscovery.com. These are the quakes of a 5 and greater magnitude for the past 24 hours. Mid-Indian Ridge had a 5.2 at 0 dark 38 this morning. That's the first on our list. 5.2 in the Mid-Indian Ridge there, right in the middle of the Indian Ocean. And then a 5.7 in the same location, a great example of an aftershock and a foreshock. So foreshock, aftershock, all occurring there within about exactly 2 hours. Papua New Guinea also had a 5.2. That was at 3:37 this morning, that 5.2 there north of Australia. Japan had a 5.1. The Chagos Archipelago had a 5.1 there. That's right near those other Indian quakes at about 8:42 Universal Time this morning. Myanmar had a 5.0. And those are the quakes of a 5 and greater magnitude. Let's get back to space, a frontier. 10.7 centimeter radial flux is now down to 142 solar flux. 143, I think it is, actually. There's the 1-year graph to contextualize the radial flux. It's the black line. See how proportional it is to the sunspot number? Yes. Yes. Next, the Space Weather Enthusiast dashboard. No geomagnetic storms in the forecast there. Again, we do have some interesting CMEs to cover. We'll get to it here. First, a little bit of Earth's magnetic moment from space for the past 4 hours. Is that what that's what we're doing? It's our geospace magnetosphere movie. Calm geomagnetic conditions are currently the earthly geomagnetic conditions. We've got fairly homogeneous magnetohydrodynamic pressure surrounding Earth right now with a slight increase in pressure on the magnetotail side, the non-sun facing side. Next Earth magnetic moment from the ground, our geospace ground magnetic perturbations map depicting Earth's magnetic moment from ground level. Again, things are mostly geomagnetically calm here, but we have had some perturbations in the solar wind, so there may be some aurora visible tonight. Make sure you share that with us over on Twitter, x.com/smashomash. Next, the planetary K-index. There you have it. 1.67 is the KP index. And here's the solar wind. Again, we did see some changes happening. We saw some intensification of the magnetic field and some changes in the other solar wind parameters. Let's skip ahead to the Discover. That was the ACE, which has a bunch of missing data. So it's dropped back down here, so it looks like a little minor CME impact happening there just recently, but it has already simmered back down. Current conditions are about 2.6 protons per cubic centimeter for the solar wind density, solar wind velocity here, about 360 kilometers per second. GOES magnetometers there showing a little spike. Strongest readings there in over a week at the GOES magnetometer, especially the GOES 18. And keep in mind it was just noontime, local time for the GOES 18, when it reached that peak. Around 135 nanotesla, registering on the GOES magnetometer in its geosynchronous near equatorial orbit. Next, our top view ecliptic plane field plot. There you go. Earth is in a south pole magnetic heliospheric sector, shown there in red. Here is our line of sight ecliptic plane field plot. We expect the south pole ecliptic plane magnetic sector to remain here for an extended period. That's the past 4 days. Here's our line of sight field plot. Also the past 4 days. Showing the solar B field, north and south polar fields in green and red respectively. Photosphere magnetism in grayscale. It's showing you a lot of things there. And finally, coronal holes, which is a feature of this segment because it's got our Particle Physicist segment, which is Ask a Particle Physicist. Yeah, coronal holes. Why are they the source of high-speed solar wind? Have you ever wondered? Well, there are some competing theories on it, so let's get to it. But first, we'll take a look at coronal holes, a great example of a trans-equatorial one. So we almost failed to put out the video, so special thanks go to Eugene, not just for making the video, but for reminding me. Because of being extremely busy around the Smash News Network, least busted name in news, we've got this well-defined trans-equatorial coronal hole, which is likely to provide some faster solar wind here, possibly geomagnetic storm conditions, in about 2 days. So that's the current situation. Coronal hole right in the Earth-facing zone. And if you're wondering if I think coronal holes, quote, cause earthquakes, the answer is no. And there's no science paper to prove that they do. So, no, I don't think they do. I don't see the physical mechanism for it. So, I don't know what to tell you. Coronal holes. The paper that a certain YouTuber wrote about it doesn't show that coronal holes cause earthquakes. So, anyway, moving on to our Ask a Particle Physicist segment. Here we go. It's about time to send the spotlight to Eugene the philosopher.
Okay, so today's question is, what is the mechanism that causes coronal holes to be the source of high-speed solar wind? And this is a really easy question to answer, at least from the mainstream, in air quotes, point of view. So on the sun, we have magnetic fields, right? In some areas of the sun, these magnetic fields connect 2 points on the surface of the sun, so they're sort of like, just wrapping the sun itself in themselves, so to speak. But in some areas, these magnetic field lines are open, what they call, I mean, they have to close somewhere. They just don't close on the sun, like immediately right here, right? So they probably go somewhere out to the edge of the heliosphere and then close like this, I assume. I don't really know. That's a question which is actually very difficult to answer, and perhaps nobody knows the answer yet. But the point is that at the scales of, let's say, 1 astronomical unit, they are open, all right? They appear so at the very least. So when the magnetic field lines just leave the sun like this, as I've told you in some of the previous segments, plasma, like the conductivity along the magnetic field line is much higher, and therefore particles can just freely move towards the Earth, in this case, along this magnetic field line. And that's it. That's why you get the faster wind from there, because there isn't much preventing it from going towards the Earth. So the slower wind originates apparently from everywhere else. There is still a good question. I know it's not part of today's discussion, but there is a good question of what accelerates the solar wind in the first place. And I'm not sure I want to talk about this, even though I'm ready to do so. But like modern explanation, so let's just talk about it for a little bit. So the modern explanation is that, how they say it, an additional unknown acceleration mechanism is present, all right? Likely it relates to magnetic fields. This could be like magnetic switchbacks, these things, right, discovered by Parker. These are, by the way, current sheets. So where you see the sudden change in magnetic field, there must be a current somewhere in between this change. So well, you see there are these zigzags. It means like there are some currents flowing kind of in perpendicular direction here. Of course, it's forbidden to talk about this in modern like heliophysics, but these are currents. Okay. Yeah, so one of the mechanisms is, for example, proposed mechanisms is damping of alpha waves, right? So alpha waves carry, these are waves of plasma, basically kind of like this actually, so like some sort of kind of like vibration of magnetic field line, kind of like a string. You may think about it like this, even though it's a very simplified description, but it's kind of like this. These are alpha waves, okay? So they carry some energy, and this energy might dissipate, and that might heat the solar wind and accelerate it, okay? That's one idea. Kind of like the modern, most plausible explanation from mainstream in air quotes. Then there are other alternative mechanisms. There is, for example, the Dreiser mechanism, which is relies on electrostatic field, okay? So, but it's not as simple as you may think. So we have so-called M-bipolar diffusion around the sun, which means like the sun is pretty strong, has a pretty strong gravitational field, right? So if you take a mixture of protons and electrons, so hydrogen plasma, so the protons and electrons have the same temperature, so the same kinetic energy. Since protons are very heavy compared to electrons, they cannot go out as fast, right? So imagine these are protons. So they kind of sink deeper in the solar gravitational field, whereas electrons can lift themselves up at the same temperature a bit higher. And what does that creates an outwards electric field, right? So the protons will be attracted to these extra electrons on the outside. And via the so-called Dreiser effect, where was it? Yeah, this electric field, it might actually produce these runaway electrons, as they call them, or Strahl electrons, non-thermal electrons. And these non-thermal electrons are kind of very fast. They go outside and create even more electrons on the outside. And these extra electrons attract protons once more. And that's what accelerates the solar wind, according to this mechanism. Okay? This is kind of a hypothesis. But it's a good one, if you ask me. Then, very recently, there was another idea by Akasofu, a very well-known guy in like magnetospheric research. So he has proposed that it's the alpha unipolar current that acts on the solar wind, since solar wind is charged particles, right? We have this, the magnetic field can act on a moving charged particle with certain force, and that's what he believes is happening. And according to his, so what do I mean by unipolar current? Well, there should be, since the sun is magnetized, it's a conductor, and it rotates, spins, there must be like a potential difference at different latitudes of the sun, and this drives this current, like a heliospheric wide current. I mean, we know the equatorial component, we know it as a current sheet, right? But the polar component, that's a better question, like where does it go to? And we know it's there, it's not a hypothesis. It has been measured that it's of the order of giga amperes, right? Where is it? Yeah, something like this. So according to this hypothesis, it's this other branch where these two connect, the current sheet and the polar return currents. This downward branch is creating a net outwards force on the solar wind. So that's another hypothesis of how solar wind can be accelerated. Yeah, well, I guess that will be all. But so yeah, returning to coronal holes, it's just open magnetic field lines. That's why you get faster wind. Why the wind is accelerated in the first place, that's a great question. But once again, not much is well known here again. There are certain hypotheses, just as I've described. Okay.
All right, so thanks once again, Eugene, for coming through with the video, reminding me about it today, and so on. That was really seat of the pants, so cheers. Although Eugene is as cool as a cucumber, make sure you respond to his fantastic video. Once again, our Ask a Particle Physicist segment by giving him a like. Head over to the Eugene the Philosopher channel and give him a subscribe if you haven't yet subscribed. He's now over 500 subscribers, so steadily making his way to 1,000. You can also subscribe to his Patreon if you want to help him out that way. Help out Eugene, subscribe to his Patreon, whatever. Press like, subscribe, share, etc. If you want to contribute to the Ask a Particle Physicist segment, you can find it at smashomash.com/forum. And there are some of the earlier submissions. And let's get into sunspots. Sunspot number is now at about 80. 85? 85 is approximately the sunspot number at the moment. A continued decline in solar activity. Oh my God, is it time to get into the bunker yet, folks? The only thing scarier than an active sun is an inactive sun. Oh, no, I'm so spooked. The sun's going to shut down, folks. Get in your bunker right away. All right, pardon my sarcasm. That's what's going on with sunspots. Not a lot of changes happening there. Here is the continuum for the past 24 hours. Again, no major changes there. So, kind of weak, but flaring has come up a little bit. Proton flux is still flatlined, no spikes despite some minor flaring. And let's move on to the X-ray flux. There you go. There is the past 3 days, and it was a C9.8 or so. It looks like it just missed the M class rating there. Very close to an M1 class flare, and of course that's where it gets fuzzy around the intersections of these magnitudinal lines. Remember, folks, a C-class flare is only 1/10 the power of an M-class flare, so they get a little fuzzy at the transitions. Anyway, here come flares in some spectacular detail. First, our 94 angstroms wavelength from Solar Dynamics Observatory. Most likely place for a large flare remains that northwestern limb, the upper right of your screen. Here we've added the 131 angstroms difference imagery to it. That'll show you some great additional detail there of plasma filamentary motions. And all of the flares in the past 24 have been from that northwestern limb. Here's an additional zoom in at 131 angstroms. The raw EUV data, extreme ultraviolet. It's a bunch of ionized iron gas in the solar corona, the sun's atmosphere. And here's an even closer zoom in at 94 angstroms. Another species of ionized iron. That's pretty sweet. And here's 131 angstroms, the same view. And let's speed this thing up since time is running out. There is the 131 angstroms difference imagery is now back along with 94 angstroms. Pretty sweet. And let's get to a star chart. There's what's going on overhead. This is our star chart for Lehigh Valley, Pennsylvania, by the way. That's skyandtelescope.org's star chart. Just press the Now button after putting in your location. If you're out after dusk tonight, you might see Saturn and Jupiter up there high in the sky in the early evening skies. And next is a solar system forecast. We'll show you where things are today, like that. Here's where things will be in a week, like that. We will have a crescent waning moon by the 5th of January. It'll already be next year as time continues to run out. Next, some photos of Uranus. Uranus, it's got a lot of moons, and some of them look like they're really far away, but I don't really know. Anyway, I don't know. There's some great imagery from James Webb Space Telescope of the gas giant. Fantastic imagery there of the outer planet. Uranus is a very interesting planet in that the way it orbits is it's kind of on its side. Its pole faces directly toward the sun almost. So it rotates in an odd way. Most planets are not quite tilted the way Uranus is tilted. Fantastic imagery there in various infrared spectra from James Webb. Next, CMEs, and we've had some. They look like they might be earthly directed. We'll get to it. We'll tell you if I think they're earthly directed. So there's the situation for yesterday. Some CMEs indeed popping off. Here's today, and you'll see some more coronal mass ejections popping off. And some of those look like the kind that could be earthly directed, so let's get to it. Here's some. We're going to add LASCO C3 here in blue over on the right. And I'm going to briefly rock this back once that plays through. I don't think we'll need the C3, but let's take a look at the C2. So we bring this back throughout the day today. So early this morning there was a CME out of the west. I believe that was from behind the southwest, the east, the left side, the east. From behind the southeastern limb. I don't think that has an earthly directed component. And then later on we had one out of the south. That was just after midday. And then finally another one out of the west. That was later in the day, more recent, still going on now. Let's take a look at our custom coronagraphs. Nope, I don't think those are earthly directed, any of them. They'll all miss Earth to the east, to the south, and to the west. Here we'll get it a little bit closer. We'll drop the C3 and we'll add the difference imagery. That's 193 angstroms, 60-minute running difference, along with 304 angstroms SDO. Great view of some plasma motions happening up here. Some plasma getting a little unstable up there in that northwestern limb. Also, the most likely place continued to be that location there for another large solar flare. So, yep, pretty sure those aren't earthly directed CMEs. Here's the raw imagery, 193 angstroms by itself. And let's blast through filaments and get to meteorology. Filaments are next. There are filaments from Cerro Tololo's ground-based hydrogen alpha telescope. Ah, yes. Filaments, filaments, filaments. A new very large one rising down there in the southeast. Check it out. That one's definitely worthy of a name. We should figure out who the guy is who played Bogdan on Breaking Bad and name that filament after him because it looks like one of Bogdan's eyebrows. Is that Bogdan's eyebrows? Did you know that actor that played Bogdan is like a nuclear physicist from Russia or something? Or from Romania or something like that? Anyway, some large filaments, including some getting unstable there in the west. And before we get to bonus features, let's take a look at the last couple of hours here from GOES 16 SUVI. And we do have some continued instability over there in that western limb right over here. The most likely place for a large solar flare and a CME at the same location right now, right around the western equatorial limb. Could be some fireworks about to kick off. Them's the facts. But that wasn't the right thing. There we go. Them's the facts. Let's get the bonus features. Satellite charging hazards are non-existent. It's smooth sailing. No surface or internal charging hazards. GOES electron flux here. Looking like it took a little dip here in the past hour or so. That's the GOES 16 and GOES 18's radiographic measurements from their geosynchronous orbits. There is the one-year graph of the electron flux, the greater than 2 mega electron volt electron fluence. Here's the forecast model. NOAA expecting flat levels here for the coming days. I would tend to agree, although in about 2 days we are expecting to see a coronal hole high-speed wind show up, so that should cause a big dip in the electron flux. Next, the layer where it's measured, the F layer of the ionosphere. Feel free to pause the video in this frame if you're not familiar with distances in kilometers. There's the ionosphere's vibrational frequency in megahertz, millions of vibrations per second. So that's the previous day. We'll also show the anomalygram. That's anomaly in megahertz from a 30-day median. No geomagnetic storms. We won't see an excessive amount of red on there. And of course, it is now summertime in the southern hemisphere. So as you would come to expect, more blue in the south than in the north. In other words, things look totally normal for the ionosphere. Sorry, if you're hoping for doomsday, we're not forecasting it based on any of the data that we're showing on the channel. We'll also show the WHAM, the whole atmosphere model, the global ionosphere nowcast. As we close out space weather with the total electron content forecast. It's free electrons to about 12,500 miles of altitude. And there it is. It's a count of free electrons from your handset up to your GPS satellite. Those free electrons cause signal refraction, hence the total electron content forecast being useful for GPS users. I've used it myself, and indeed it does somewhat work. We'll close out space weather with the latest high-res images. That's what's going on. And let's get to meteorology. Meteorology. Another thing that we do as a value-added feature. Yesterday we looked at the coldest place in the world, and we got some interesting comments on Twitter about it. Maybe go check us out over there at x.com/smashomash. Today, some of the hottest water in the world. Where do you think that's located? That, my friends, foes, and neutrals, is the equatorial Pacific Ocean, where the water's 87.4 degrees. Why are we showing this? Because there's an atmospheric river showing up in California. And all of that convective ability. Excuse me. All of that convective ability of all that hot water contributes to the water showing up in California. Some of that is vaporized Pacific Ocean water, folks. Anyway, let's move to our regularly scheduled meteorology segment. There are the surface winds of the east. These are the jet streams. Shout out to our viewers from this side of the planet. Here are the jet streams of the central world. Shout out to our viewers from there. Here are your surface winds. Shout out to our viewers from the western world. There are our surface winds, and here are the jet streams. Yeah, the jet stream, it carries specific moisture into California sometimes, like now. So here you'll get a view of that. It's clouds and fog over the Americas. Yes, clouds and fog, my friends and foes and neutrals. People who just don't care, that's a thing too. If you choose not to decide, you still have made a choice. Anyway, here are some of the headwaters of that atmospheric river that's making landfall there around San Francisco. That's where all those gloomy skies are coming from. The equatorial Pacific's hot convective water becoming water vapor, Earth's most powerful greenhouse gas. I guess that's too controversial. Maybe I shouldn't say such things, folks. Anyway, here's our precipitation type map, courtesy of windy.com, who also endorses absolutely nothing that I say. So don't hold them responsible for the things I say. Windy.com, hold yourself responsible for knowing what's going on with the weather. It's our precipitation type map, as there is some freezing rain showing up in Maine. Freezing rain in Maine on the plain is something that if you're using your brain, you won't go driving in. Next, our weather.gov map, weather.gov, and we've got some frost advisories in Georgia and Florida as some Gulf state cold weather showing up. Weather.gov, if your location is lit, that's too many counties to cover, but we can show you the ball drop forecast. Yeah, the ball drop forecast. No, I don't mean your children becoming a man. I mean the New Year's Eve ball. That's where things will be in 54 hours at zero dark, whatever, 0 dark 0 on January 1st, 2024. So that's about the temperature map that you'll be seeing for is that universal time? That's universal time, folks. So that's actually a little bit before midnight here, like 4 hours. So it'd be more like that. I don't know. Whatever. I'm not doing the math. I'm not doing the math. You do the math. And let's get to our temperature anomaly forecast in degrees Celsius. So there you go. There's where you can expect temperatures to be into next year. That should be an accurate forecast, by the way. We don't show forecasts beyond 3 days because those aren't accurate. Next, total accumulated precipitation in inches. Heaviest rain coming to California for the coming 3 days. 72-hour GFS forecast is what we're showing. Next, the accumulated positive snow depth change in inches. Same model, GFS 72-hour. And last but not least, the pressure and precipitation forecast. Pressure and precipitation based on the same model, the GFS 72-hour model. Yeah, California's going to get pretty plastered there with that moisture from the Pacific. Next, lightning. And there's a continued lightning storm there in the subtropical Atlantic Ocean. That's the past about 10 hours as the storm rages on, making for bad times for sailors like Marky Mark Wahlberg and George Clooney. There's nothing hunkier than seeing guys killed by waves. I mean, it's so hunky. Those hunks just make me want to watch The Perfect Storm. What about you? Let us know in the comments. And let me know if there's a Calvin Klein underwear ad dovetailed into the film by Marky Mark. Let us know in the comments. Anyway, that's a real-time lightning map from lightningmaps.org. We'll close out with telling you to press the like button, or else your soul shall be cast into a demonic spouting, which is all plugged up with starling nests. Is that what you want for your soul to happen? Plugged up in starling nests? Of course not. That's no way to reach the river Styx. So press the like button. Visit us on Twitter. You can visit our homepage at smashomash.com. And welcome to the Neo Renaissance, by the way. Congratulations on realizing the channel exists. We're flabbergasted. We're going berserk over the fact that you found the channel, so congratulations on that. Press the subscribe button if you're new. And if you haven't pressed like yet, you may want to press like, or we will do things. We will do completely harmless things that are of absolutely no danger to you whatsoever. Anyway, there is the Doppler radar for the full 50 states. We're closing out with the lower 48s. Doppler, clouds and fog. And don't forget water vapor. Yeah, it shows dry air, which is more massive than moist air. Did you know this? Were you aware that dry air is more massive than moist air at a given atmospheric pressure? Dry air is more moist. Yes, that's what I meant. Anyway, there is the U.S. Doppler radar map. Because this is your recap. There is your satellite view of clouds and fog, shortwave radiation, 3.9 micrometers. And there is the water vapor map, which shows you not just clouds. It shows you dry air. It shows you moist air. And here's me getting out of here since time is running out. I've got to get back to the bunker and consume a bunch of stale MREs. I'm going back to the bunker again. I pretend I like this food based on advice from Ben. Oh.